Right. Third in the series now, just to finish up the mechanisms. The others, basically, they're not called nucleophilic or electrophilic anything. Then there's two that are closely related. Those are the hydration and dehydration mechanisms. And then there's the haloalkane one where you make an alkene. So I've stripped them down to the bare bones this time. Obviously, it doesn't matter what the rest of the structure looks like. Catchphrase coming your way now. Whenever it's alkene related, as all three of these are, you're always working across two carbons. Okay, so the conditions for elimination of a haloalkane, it involves NaOH. Okay, NaOH with its hydroxide ion there. The hydroxide ion can act as a nucleophile, where it simply swaps place with the Br. So that's just two arrows. We had that one earlier. Or what we've got here, when the hydroxide ions are more concentrated and usually in quite a harsh solvent like in ethanol, what we have is instead the hydroxide acts as a base. So unnecessarily curly arrow there, but it bonds to a H, which is on a carbon, which is next door to the CBr. The CH bond breaks and goes into reinforcing the CC. That's going to double it up to make the double bond. Good leaving group leaves, Br leaves as a bromide ion. So whatever these other groups were, I'm just leaving them trailing, the idea is that the H gets taken away by the hydroxide as a H2O. Double bond, that's this second arrow here happening or forming the double bond. Again, whatever those attachments were, they're still there, and a bromide ion gets kicked out. So NaOH comes in, NaBr goes out, for example. That's all there is there. That's a pretty silly arrow. Okay, working across two carbons. Now these two are closely linked. They're both acid catalyzed. I'd suggest that you want to use phosphoric acid as the catalyst if you're asked for one. It could be conch sulfuric, that's fine as well. The only confusion is we've got a different mechanism that involves an alkene undergoing electrophilic addition with conch sulfuric acid, and that's fine, but that's not the one we're talking about here. So maybe if you want to just put a distinction between them, use conch phosphoric for this. The H plus that starts this mechanism off is from that catalyst. Okay, it's conch, which means there's nowhere for that H plus to go because it's not dissolved in loads of water. The alkene bonds to it. That immediately breaks the double bond, replacing it with a single bond. One of the two double bond carbons inherits that H. The other of those two inherits the positive charge. And again, there might be a major minor consideration there depending on what's attached. The more stable carbocation is more likely to form. Now, at this point, H2O comes along in the form of steam. Okay, this is happening at high temperature. And uses its lone pair to bond to the C+. That gives us a second intermediate. So the acid catalyst H is still on that first carbon. Now we've got an OH2 plus group on the other carbon. Just like in other mechanisms, you see an O with 3 bonds, stick a plus on it, and it's definitely correct. Now we know this is acid catalyzed. We need to replace the H plus that's been used up. It's actually not the same H that comes back. It's one of these water hydrogens. So an arrow has to come from the OH bond. It has to go to the O plus. So there we are. That gives us our product. So CC double has put a H onto the one carbon and an OH onto the other. It wasn't actually the H and OH both from water. The H was from the catalyst, the OH was from the water. And the missing hydrogen also from water goes off to replace the catalyst. So there's no net change in the total amount of H plus that's present. Okay, there it is. Now dehydration, we follow these same intermediates, but in the opposite order. So we're going to start with OH. We're going to go to an OH2 plus, which will then drop off to give a C plus, which will then lead to the alkene. So the arrows are different, but it's the same structures throughout. I will do it anyway. Again, we're working across two bonds, which is why I'm going to show two carbons, okay, because I'll need them. Again, whatever's attached here, you get the idea. It could be anything. It doesn't make a difference. There's at least one lone pair. There are two lone pairs on that O. Just show one of them because there's an arrow coming from it. And it's acid catalyzed, so there's the H plus that's going to kick it all off. So that bonds to the H plus, giving us the OH2 plus intermediate. That H that I'm drawing there is, as you might expect, it's about to have something happen to it, even though I don't really need to have expanded it out just yet. There we are. What happens next? We need to form a C plus. Okay, I've remembered that. So it must be that I need an arrow basically showing the H2O fall off. So the hydroxyl group, the alcohol group, has been turned in, again, to a good leaving group, to a water molecule, which then happily just drops off. An arrow going from the CO bond to the O+, okay, again. Leaving behind a carbocation. What happens next? Well, ultimately, we're headed towards an alkene. We need to sort out this positive charge, and we know that this carbon needs to lose an atom in order to make way for the double bond. So the CH bond has to break, something like that. Okay, from the CH bond to the CC bond, this bonding pair gets redeployed as a bonding pair between those two atoms instead of these two atoms. And there it is. That means, again, that this H here has replaced the catalytic H+, that was used up at the very beginning. There's our alkene. The final thing on this, so it's a reversible reaction then. We've got an alkene plus steam, acid catalyzed. Remember, conch phosphoric is a good shout there to give an alcohol. I've drawn that slightly weirdly, but there we are. Okay, so it's reversible. This is all happening in the gas phase. So Le Chatelier's principle is relevant if it was a question about equilibrium shift or whatever, and so on. Okay, hopefully that helps.